Right now on the hellish surface of Venus, something impossible is happening that defies every intuition you have about how planets should work. A single day on Venus, the time it takes the planet to rotate once on its axis, lasts 243 Earth days, while a complete year on Venus, the time it takes to orbit the Sun once, lasts only 225 Earth days. This means that a day on Venus is actually longer than a year on Venus, creating a world where the Sun rises and sets less than twice per year. This isn't just a curious astronomical fact. It is evidence of a planetary catastrophe so severe that it literally turned an entire world upside down, creating conditions so alien that they challenge our understanding of how planets can exist and evolve in our solar system. To understand just how bizarre this situation is, imagine if Earth behaved the same way. You would wake up in the morning, and the sun would rise so slowly that it wouldn't set again until after you'd experienced an entire year of seasons, spring, summer, autumn, and winter would all pass while the sun moved from sunrise to sunset. By the time that single day finally ended, you would have aged a full year. But Venus's temporal impossibility goes even deeper. Not only does Venus rotate incredibly slowly, but it rotates backwards compared to almost every other planet in the solar system. While Earth rotates from west to east, making the sun appear to rise in the east and set in the west, Venus rotates from east to west, making the sun rise in the west and set in the east. If you could see the sun through Venus's impenetrable atmospheric clouds. Dr. Carl Sagan's research on planetary atmospheres revealed that Venus represents perhaps the most extreme example of planetary evolution gone wrong in our solar system. What should have been Earth's twin, similar in size, mass, and distance from the sun, instead became a scorching hellscape with surface temperatures hot enough to melt lead and atmospheric pressures 90 times greater than Earth. The mathematical reality of Venus's rotation is staggering. Venus completes one rotation relative to the stars every 243.025 Earth days. But because it's also moving in its orbit around the sun, a solar day on Venus, the time from one sunrise to the next, lasts approximately 116.75 Earth days. This means that on Venus, you experience only about 1.9 sunrises and sunsets per Venusian year. Recent observations from NASA's Parker Solar Probe and the European Space Agency's Venus Express mission have revealed that Venus's atmospheric dynamics are just as bizarre as its rotation. The planet's atmosphere rotates much faster than the planet itself, creating winds that circle the planet in just 4 Earth days, a phenomenon called superrotation that remains one of the great unsolved mysteries in planetary science. This atmospheric superrotation means that while Venus's surface takes 243 days to complete one rotation, the clouds above race around the planet 60 times faster, creating a world where the atmosphere and surface exist in completely different temporal regimes. It is as if Earth's atmosphere decided to ignore Earth's rotation entirely and spin at its own wildly accelerated pace. The implications of Venus's temporal distortion extend far beyond mere curiosity. Understanding how Venus became locked in this slow backwards rotation provides crucial insights into planetary formation, the evolution of atmospheric dynamics, and the delicate balance of forces that determine whether a planet becomes habitable or becomes a toxic wasteland. Dr. Dave Stevenson's research on planetary dynamics suggests that Venus's current state might result from catastrophic events early in solar system history, possibly including massive impacts, tidal interactions, or atmospheric evolution processes that gradually slowed and reversed the planet's rotation over billions of years. The greenhouse effect on Venus creates a feedback loop that may have contributed to its current rotational state. Recent computer simulations by Dr. Alexander Correa at the University of Aveiro suggest that Venus may have experienced a runaway greenhouse effect that not only made its surface uninhabitable, but also fundamentally altered its rotational dynamics through complex interactions between atmospheric heating tidal forces from the Sun and internal planetary structure changes. The absence of a moon around Venus adds another layer to this mystery. Earth's moon plays a crucial role in stabilizing our planet's rotation and tilt, but Venus lacks this stabilizing influence. Without a large moon to regulate its rotation through tidal interactions, Venus may have been more susceptible to the processes that eventually slowed and reversed its spin. Dr. Jacques Lasker's research on planetary dynamics shows that planets without substantial moons can experience chaotic variations in their rotational states over geological timescales. Venus' current rotation might represent just one phase in a complex evolutionary process that could continue changing over millions or billions of years. If you're fascinated by the extreme physics of planetary dynamics, subscribe and hit the thumbs up button. And here is a mind-bending question to consider. If you could live on Venus and experience days longer than years, how do you think human civilization would adapt its concepts of time, seasons, and daily life? Comment your most creative ideas below. I'll pin the most thoughtful answer. The story of Venus's impossible rotation touches on fundamental questions about how planets form, evolve, and maintain their characteristics over cosmic timescales. Why did Venus become so different from Earth, despite their similar origins? What forces can slow a planet's rotation to almost nothing and then reverse its direction entirely? And what does Venus's current state tell us about the future evolution of all planets, including our own? Tonight, we're going to explore one of the solar system's most profound mysteries: how a world that should have been Earth's twin instead became a backwards, slow-spinning furnace that challenges our understanding of planetary physics and offers sobering lessons about how quickly and dramatically planetary environments can change. The journey ahead will take us from the formation of the solar system through the catastrophic processes that shaped Venus, into the extreme atmospheric dynamics that continue to drive its evolution today, and finally to the implications of Venus's story for our understanding of planetary habitability throughout the universe. Consider this: Venus's temporal distortion isn't just an astronomical curiosity. It has a window into planetary physics, operating under the most extreme conditions, revealing how the same gravitational and atmospheric forces that created Earth's benign environment can, under slightly different circumstances, create worlds that exist in completely different relationships with space and time. Now let's begin our exploration of how Venus became the planet where time itself behaves impossibly, and what this reveals about the hidden dynamics that determine whether worlds become paradises or prisons. Chapter 1. Backwards World. The first thing you need to understand about Venus's impossible rotation is that it represents one of the most profound anomalies in our solar system. World that spins backwards so slowly that it challenges every model of planetary formation and evolution we've developed. Venus doesn't just rotate differently from Earth. It rotates in the opposite direction from almost every other major body in the solar system, creating a planet where the very concept of normal planetary behavior breaks down entirely. In a solar system where nearly everything rotates in the same direction, a consequence of the angular momentum inherited from the original solar nebula that formed our solar system 4.6 billion years ago, Venus stands alone as a world that somehow reversed its spin. This retrograde rotation means that if you could stand on Venus's surface and see through its dense clouds, the sun would rise in the west and set in the east, opposite to the familiar pattern we observe on Earth. Dr. Harold Levison's research on solar system formation reveals that when the solar nebula collapsed to form the sun and planets, conservation of angular momentum ensured that almost everything would spin in the same direction. The sun rotates in this direction. All the planets except Venus orbit in this direction, and most planets rotate on their axes in the same direction. Venus's retrograde rotation is so unusual that that it suggests catastrophic events fundamentally altered the planet's spin sometime after its formation. The mathematical description of Venus's rotation involves what astronomers call a retrograde rotation period of 243.025 Earth days. This measurement represents the time Venus takes to complete one full rotation relative to the stars, what astronomers call a sidereal day. But because Venus is moving in its orbit around the Sun while it rotates, the time between successive sunrises on Venus, the solar day, is different from the sidereal day. Recent precise measurements from radar observations conducted by NASA's Deep Space Network have refined our understanding of Venus's rotation period with extraordinary accuracy. These observations reveal that Venus's rotation is not only retrograde, but also remarkably stable, varying by less than a few minutes over decades of observation. The discovery of Venus's retrograde rotation came gradually through telescopic observations that began in the 17th century but weren't definitively confirmed until radar astronomy became possible in the 1960s. Venus's dense cloud cover makes optical observation of surface features impossible, so astronomers had to wait for radar technology to penetrate the clouds and reveal the planet's true rotational characteristics. Dr. Richard Goldstein's pioneering radar observations at NASA's Jet Propulsion Laboratory in 1962 provided the first definitive measurements of Venus's rotation period and direction. These observations shocked the astronomical community because they revealed rotation characteristics completely unlike any other planet in the solar system. The comparison with Earth's rotation highlights just how extreme Venus's situation has become. Earth completes one rotation in approximately 23 hours and 56 minutes, rotating in the same direction as its orbital motion around the Sun. This alignment between rotational and orbital motion is what most planetary formation models predict for planets forming from rotating solar nebulae. Venus's backwards rotation creates a unique relationship between its day and year that has no parallel anywhere else in the solar system. While Earth experiences approximately 365.25 days per year, Venus experiences only about 1.92 solar days per year, meaning that sunrise occurs less than twice per Venusian year. The gravitational implications of Venus's slow retrograde rotation affect many aspects of the planet's physical behavior. The rotation rate of a planet influences its magnetic field generation, atmospheric dynamics, and internal heat distribution. Venus's extremely slow rotation contributes to its lack of a significant magnetic field and creates atmospheric circulation patterns unlike those on any other planet. Dr. David J. Stevenson's research on planetary magnetism shows that planetary magnetic fields are typically generated by the motion of conducting fluids in a planet's interior, a process called the dynamo effect. This process requires sufficient rotation to create the convective motions needed for magnetic field generation. Venus's slow rotation makes dynamo action much less efficient, contributing to the planet's weak or absent magnetic field. The atmospheric consequences of retrograde rotation are equally profound. The Coriolis effect, which influences weather patterns on all rotating planets, operates in the opposite direction on Venus compared to prograde rotating planets. This reversed Coriolis effect contributes to Venus's unique atmospheric circulation patterns, including the mysterious superrotation of its upper atmosphere. Recent atmospheric modeling by Dr. Scott Rafkin at the Southwest Research Institute suggests that Venus's retrograde rotation interacts with solar heating patterns to create atmospheric dynamics that are fundamentally different from those on Earth or any other planet. These dynamics might contribute to maintaining Venus's extreme greenhouse conditions and dense atmospheric pressure. The tidal interactions between Venus and the Sun are also affected by the planet's unusual rotation. Tidal forces from the Sun create bulges in Venus's shape that interact with the planet's rotation in complex ways. For a retrograde rotating planet, these tidal interactions can either further slow rotation or potentially even reverse it back to prograde rotation under certain conditions. Dr. Jacques Lasker's long-term dynamical studies of Venus rotation show that the planet's current state might not be permanent. Over millions of years, tidal interactions with the Sun could continue to modify Venus's rotation, potentially leading to further changes in rotation period or even direction. The discovery of Venus's retrograde rotation has implications beyond just understanding Venus itself. It demonstrates that planetary rotation states can change dramatically over geological timescales through processes that we're still working to understand. This has implications for our understanding of exoplanets and the variety of rotational states that planets might exhibit throughout the universe. Recent observations of exoplanets have revealed many with unusual rotational characteristics, including tidally locked planets that always show the same face to their stars and planets with extreme axial tilts. Venus's retrograde rotation shows that our own solar system contains examples of these exotic rotational states, providing natural laboratories for understanding planetary dynamics under extreme conditions. The surface temperature distribution on Venus is also affected by its retrograde rotation, though not in ways that are immediately obvious due to the planet's extremely dense atmosphere. The slow rotation means that day-night temperature differences would be extreme if Venus had a thin atmosphere like Earth's. However, Venus's thick atmosphere redistributes heat so efficiently that day-night temperature differences are minimal despite the long solar days. Dr. James Pollock's research on Venus's atmospheric dynamics reveals that the planet's slow rotation allows the atmosphere to redistribute heat from day to night sides so effectively that surface temperatures remain nearly constant around the planet. This efficient heat redistribution contributes to maintaining the extreme greenhouse conditions that make Venus's surface uninhabitable. The study of Venus's retrograde rotation provides insights into the complex feedback loops that can develop between planetary rotation, atmospheric dynamics, and surface conditions. These feedback loops can lead to stable states that are very different from what we might expect based on initial planetary formation conditions. Recent computer simulations by Dr. Mark Bullock at the Southwest Research Institute explore how Venus's current retrograde rotation state might be maintained through interactions between atmospheric dynamics, solar tidal forces, and internal planetary structure. These simulations suggest that Venus's current state might represent a stable equilibrium that could persist for billions of years. The philosophical implications of Venus's backwards rotation challenge our assumptions about planetary normality and highlight the diversity of possible planetary states. Venus demonstrates that planets can evolve in ways that take them far from their initial formation conditions, creating worlds that operate according to completely different physical principles than those we observe on Earth. Understanding Venus's retrograde rotation also provides crucial context for assessing planetary habitability. The same forces that created Venus's backwards rotation might also contribute to its extreme greenhouse conditions and lack of surface water. This suggests that rotational characteristics might be important factors in determining whether planets can maintain habitable conditions over geological timescales. As we prepare to explore the mysterious processes that might have created Venus's retrograde rotation, remember that this backwards world represents more than just an astronomical curiosity. It is evidence that planets can undergo transformations so profound that they fundamentally alter their relationship with space and time, creating worlds that challenge our basic assumptions about how planetary systems should work. Chapter 2: Retrograde Mystery. The question of how Venus acquired its backwards rotation represents one of the most challenging puzzles in planetary science, involving processes so violent and transformative that they could reverse the spin of an entire planet over geological timescales. The leading theories for Venus's retrograde rotation involve catastrophic impacts, complex tidal evolution, or atmospheric dynamics operating over billions of years, each suggesting that planets can undergo changes so dramatic that they rewrite their fundamental physical characteristics. The giant impact hypothesis represents the most straightforward explanation for Venus's retrograde rotation, proposing that early in solar system history, Venus collided with a massive object that completely reversed its original rotation direction. Dr. Alistair Cameron's research on planetary collisions during the solar system's formation period suggests that such large impacts were common during the first few 100 million years after planetary formation. Computer simulations of giant impacts on Venus-sized planets by Dr. Robin Canop at the Southwest Research Institute reveal that an object with roughly 10 to 15% of Venus's mass striking at the right angle and velocity could indeed reverse the planet's rotation. Such an impact would need to be nearly head-on to be effective, suggesting that if this mechanism created Venus's retrograde rotation, it represents an extremely unlikely but not impossible event. The collision scenario becomes more complex when considering the consequences beyond just rotational reversal. A giant impact large enough to reverse Venus's rotation would have melted much of the planet's surface, created a massive debris disk around the planet, and potentially stripped away any early atmosphere that Venus might have possessed. The lack of a substantial moon around Venus might actually support this theory. The impact might have been so violent that any debris was either recaptured by the planet or ejected completely from the Venus system. Recent isotopic analysis of Venus' atmosphere by the Venus Express mission has revealed clues that might support or refute impact scenarios. Dr. Sushil Atreya's research on Venus's atmospheric composition shows ratios of noble gases that could be consistent with atmospheric loss during massive impact events, though alternative explanations for these ratios also exist. Tidal evolution represents a more gradual mechanism for creating retrograde rotation through interactions between Venus, the Sun, and potentially other planets in the solar system. Dr. Alexander Correa's research on tidal dynamics shows that if Venus originally had a thick atmosphere and rotated more rapidly, solar tides acting on atmospheric mass could gradually slow the planet's rotation and eventually reverse it. This tidal scenario requires specific conditions to work effectively. Venus would need to have developed its thick atmosphere early in its history, and the atmospheric density would need to be sufficient to create substantial atmospheric tides when heated by solar radiation. The process would operate over hundreds of millions to billions of years, gradually transferring angular momentum between Venus's rotation and its orbital motion around the Sun. The mathematical modeling of atmospheric tidal evolution involves complex calculations of how solar heating creates density variations in Venus' atmosphere and how these variations interact with the planet's rotation to transfer angular momentum. Dr. Tim Donahue's research on Venus atmospheric evolution suggests that this process could account for both Venus' slow rotation and its retrograde direction, though the calculations require very specific atmospheric conditions to work. Resonance capture represents another possible mechanism where Venus's rotation becomes locked in a specific relationship with its orbital period through gravitational interactions. Dr. Jack Wisdom's research on planetary dynamics shows that planets can become trapped in spin-orbit resonances, where their rotation periods are simple ratios of their orbital periods. For Venus, the current rotation period of 243 days is very close to creating a specific resonance with Earth's orbital period. When Earth and Venus are closest together during inferior conjunction, Venus shows nearly the same face to Earth each time. This near resonance might not be coincidental, but could represent evidence that Venus's rotation has been shaped by gravitational interactions with Earth over geological timescales. The resonance mechanism requires that Venus's rotation was gradually slowed by some process, possibly atmospheric tides or other tidal forces, until it became captured in a resonance with either the Sun or Earth. Once captured in such a resonance, Venus's rotation would be stabilized at its current period and direction, potentially explaining both the magnitude and retrograde nature of Venus's current rotation. Recent computational studies by Dr. Gwenelle Bouet at IMCC in Paris explore how multiple resonance effects between Venus, Earth, and the Sun might interact to create Venus's current rotational state. These studies suggest that Venus's rotation might represent a complex equilibrium between several different gravitational influences operating simultaneously. Core mantle coupling represents an internal mechanism where changes in Venus's internal structure could affect its rotation over geological timescales. Dr. Bruce Buffett's research on planetary core dynamics shows that interactions between a planet's molten core and solid mantle can transfer angular momentum and potentially change rotation rates and directions. If Venus experienced significant changes in its internal structure, perhaps through extensive volcanism, core crystallization, or other geological processes, these changes could affect the efficiency of core mantle coupling and potentially alter the planet's rotation. This mechanism would require very specific internal evolution scenarios and might work in combination with external tidal forces rather than operating alone. The atmospheric evolution scenario proposes that Venus's thick atmosphere and extreme greenhouse conditions develop gradually over geological time, and that this atmospheric evolution somehow drove changes in the planet's rotation. Dr. David Grinspoon's research on Venus climate evolution explores how runaway greenhouse effects might create atmospheric conditions that interact with planetary rotation in unexpected ways. This scenario suggests that as Venus's atmosphere thickened and temperatures increased, atmospheric dynamics might have created net torques on the planet that gradually changed its rotation. The mechanism would require very specific atmospheric circulation patterns and might involve interactions between atmospheric superrotation, surface friction, and tidal forces from the Sun. Recent atmospheric modeling by Dr. Lee Lewis at Trinity University explores how Venus's superrotating atmosphere, which circles the planet much faster than the surface rotates, might interact with surface topography and atmospheric heating to create torques that affect planetary rotation over long timescales. The possibility of multiple mechanisms operating simultaneously represents the most complex but potentially most realistic scenario for Venus's retrograde rotation, rather than resulting from a single catastrophic event or gradual process. Venus's current rotation might reflect the combined effects of early impacts, long-term tidal evolution, atmospheric dynamics, and internal planetary changes operating over billions of years. Dr. James Pollock's comprehensive studies of Venus evolution suggest that the planet's current state reflects a complex history where multiple processes interacted to create conditions that are stable, but very different from those on other terrestrial planets. Understanding this evolution requires considering the entire system of interactions between Venus's interior, surface, atmosphere, and external gravitational influences. The observational evidence for different retrograde formation mechanisms remains limited, because most potential evidence has been erased by Venus's subsequent geological and atmospheric evolution. The planet's extreme surface conditions and geological activity have eliminated most traces of early impact events, while atmospheric evolution has obscured evidence for gradual rotational changes. Future missions to Venus, including NASA's planned Da Vinci Plus and Veritas missions and ESA's Envision orbiter, might provide new constraints on retrograde rotation mechanisms through detailed studies of Venus's internal structure, atmospheric composition, and surface geology. These missions could reveal isotopic signatures, gravitational field variations, or geological features that provide clues about Venus's rotational history. The study of Venus's retrograde rotation also provides insights into the diversity of possible planetary evolution pathways throughout the universe. If planets can undergo rotational reversals through various mechanisms, then exoplanet systems might contain many worlds with exotic rotational characteristics that we're only beginning to understand. Recent discoveries of exoplanets with unusual rotational properties, including tidally locked planets and planets with extreme axial tilts, suggest that Venus-like rotational evolution might be common in planetary systems. Understanding how Venus acquired its retrograde rotation provides crucial context for interpreting these exotic exoplanet observations. As we prepare to explore Venus's atmospheric prison and its role in the planet's extreme conditions, remember that the mystery of retrograde rotation represents more than just a puzzle about planetary dynamics. It is a window into the complex, often violent processes that can reshape entire worlds and demonstrates that planets can evolve in ways that fundamentally alter their basic physical characteristics. Chapter 3. Atmospheric prison. Surrounding Venus, like an impenetrable blanket, lies an atmospheric prison so dense and corrosive that it creates surface pressures 90 times greater than Earth, as while trapping heat so effectively that surface temperatures exceed 460 degrees Celsius, hot enough to melt lead. This crushing atmospheric envelope doesn't just make Venus uninhabitable. It fundamentally alters the planet's relationship with time and rotation, creating feedback loops between atmospheric dynamics and planetary spin that might help explain why Venus rotates backwards and so slowly. The sheer mass of Venus's atmosphere is staggering, roughly 90 times more massive than Earth's entire atmosphere, composed primarily of carbon dioxide with clouds of concentrated sulfuric acid that completely obscure the planet's surface from optical observation. Dr. Carl Sagan's pioneering research on Venus's greenhouse effect revealed that this dense atmosphere creates the most extreme greenhouse conditions in the solar system, with surface temperatures that remain nearly constant day and night despite Venus's extremely long solar days. The atmospheric pressure on Venus's surface reaches approximately 9.2 megapascals, equivalent to the pressure you would experience nearly a kilometer underwater on Earth. This crushing pressure is sufficient to implode most spacecraft not specifically designed for Venus conditions, and it creates a surface environment where the atmosphere behaves more like a dense fluid than a gas, affecting everything from heat transport to mechanical interactions with the solid planet. Dr. James Pollock's comprehensive atmospheric models demonstrate that Venus's dense atmosphere creates thermal conditions so extreme that they significantly affect the planet's rotational dynamics. The massive thermal expansion and contraction of the atmosphere as different regions are heated by solar radiation can create atmospheric tides, periodic bulges in atmospheric mass distribution that interact with the planet's rotation through gravitational and frictional forces. These atmospheric tides operate on Venus through mechanisms unlike those on any other planet. Earth's atmosphere creates tidal bulges that are relatively small compared to ocean tides, but Venus's atmosphere is so massive that atmospheric tidal effects can be substantial. Solar heating creates atmospheric density variations that move around the planet, creating moving mass concentrations that can exert torques on the planet's rotation. Recent atmospheric modeling by Dr. Scott Rafkin shows that Venus's atmospheric tides might play a role in maintaining the planet's slow rotation period. As the sun heats different parts of Venus's atmosphere, the thermal expansion creates atmospheric bulges that are slightly offset from the direct solar heating, point due to the time required for thermal response. These offset bulges create torques that can either accelerate or decelerate planetary rotation. The superrotation of Venus's upper atmosphere adds another layer of complexity to the atmospheric prison. While Venus's surface takes 243 Earth days to complete one rotation, the upper atmosphere circles the planet in just 4 Earth days, a factor of 60 faster than the surface. This atmospheric superrotation represents one of the most extreme examples of atmospheric solid-body decoupling in the solar system. Dr. Gerald Schubert's research on Venus' atmospheric superrotation reveals that this phenomenon involves complex interactions between solar heating, atmospheric chemistry, and global circulation patterns that are still not fully understood. The superrotating atmosphere effectively isolates the surface from direct interaction with space, creating a massive buffer that affects how external forces influence the planet's rotation. The atmospheric composition of Venus contributes to its prison-like characteristics through chemical processes that are both corrosive and thermally extreme. The atmosphere is approximately 96.5% carbon dioxide and 3.5% nitrogen, with trace amounts of sulfur dioxide, water vapor, carbon monoxide, and other compounds that create a chemically hostile environment unlike anything on Earth. The sulfuric acid clouds that perpetually shroud Venus form through chemical reactions involving sulfur dioxide, water vapor, and atmospheric dynamics that concentrate these compounds at altitudes between 50 and 70 kilometers above the surface. Dr. Larry Esposito's research on Venus cloud chemistry shows that these clouds are so concentrated that they would cause severe chemical burns to any exposed material, while also contributing to the atmospheric mass that affects planetary dynamics. The greenhouse effect on Venus operates through multiple atmospheric layers that trap thermal radiation with extraordinary efficiency. Solar energy penetrates the atmosphere and heats the surface, but the dense carbon dioxide atmosphere prevents most thermal radiation from escaping back to space. This creates a runaway greenhouse effect that is stabilized at temperatures where thermal radiation emission finally balances solar energy absorption. Dr. James Casting's climate modeling research demonstrates that Venus' atmospheric greenhouse effect is so extreme that it creates positive feedback loops that make the system remarkably stable despite its extreme conditions. Once established, the dense atmosphere maintains its own existence by preventing the surface cooling that would be necessary for atmospheric condensation and pressure reduction. The atmospheric dynamics on Venus create wind patterns that are both extreme and puzzling. Surface winds are relatively gentle, typically only a few kilometers per hour due to the high atmospheric density, but upper atmospheric winds can exceed 350 kilometers per hour in the superrotating circulation system that encircles the planet. Recent observations from the Venus Express mission revealed that these atmospheric circulation patterns include phenomena like atmospheric tornadoes at the poles, massive cloud vortices that persist for years, and atmospheric waves that propagate through the dense atmosphere in complex patterns that affect global atmospheric dynamics. The interaction between Venus' atmospheric prison and its slow rotation creates unique thermal distribution patterns that have no analog on other planets. Despite solar days lasting 117 Earth days, Venus' surface temperature remains nearly constant around the planet due to the atmosphere's extraordinary efficiency at redistributing heat from day to night sides. Dr. David Grinspoon's research on Venus thermal dynamics shows that the atmosphere transports heat so effectively that day-night temperature differences are only a few degrees Celsius, even though the slow rotation means that any given surface location experiences 58.5 Earth days of continuous sunlight, followed by 58.5 Earth days of darkness. The atmospheric prison concept extends beyond just physical containment to include temporal effects that alter how Venus experiences time itself. The dense atmosphere creates such effective thermal buffering that seasonal variations, which depend on thermal response to orbital position changes, are essentially eliminated. Venus exists in a state of perpetual thermal equilibrium that isolates it from the temporal variations that characterize most other planets. The atmospheric mass loading on Venus' rotation represents a subtle but potentially important effect where the atmosphere's momentum affects the planet's rotational Dynamics. Dr. Raymond Peary Humbert's atmospheric physics research explores how the mass and motion of Venus' atmosphere might couple to the solid planet's rotation through friction, gravitational effects, and momentum exchange at the surface-atmosphere interface. This atmospheric rotational coupling could help explain why Venus's rotation has stabilized at its current slow retrograde rate. If the atmosphere gains significant angular momentum through solar heating effects or other processes, this momentum would need to be balanced by changes in the solid planet's rotation to conserve total system angular momentum. The chemical interactions between Venus's atmospheric prison and its surface create additional complexities that affect long-term planetary evolution. At the extreme surface temperatures and pressures on Venus, many chemical reactions occur that would be impossible under Earth-like conditions, potentially affecting surface composition and atmospheric chemistry in ways that influence planetary dynamics over geological timescales. Recent spectroscopic analysis of Venus's lower atmosphere by the Akatsuki orbiter has revealed chemical gradients and reaction products that provide insights into surface-atmosphere interactions under extreme conditions. These observations suggest that Venus' atmospheric chemistry continues to evolve through processes that might affect the planet's rotational and thermal evolution over millions of years. The atmospheric prison model for Venus provides crucial insights into how extreme atmospheric conditions can create stable planetary states that are radically different from Earth-like conditions. Understanding these processes is essential for assessing the habitability of exoplanets, particularly those that might have undergone runaway greenhouse effects similar to Venus. The study of Venus's atmospheric prison also demonstrates how atmospheric and rotational evolution can become coupled through complex feedback mechanisms that operate over geological timescales. These insights are crucial for understanding planetary evolution throughout the universe and for assessing how planets respond to changing conditions over cosmic time. As we prepare to explore the tidal forces that shape Venus's rotation, remember that the atmospheric prison surrounding Venus represents more than just an extreme environment. It is a complex system that actively participates in determining the planet's rotational characteristics and demonstrates how atmospheric evolution can fundamentally alter a planet's relationship with space and time. Chapter 4. Tidal Forces. Invisible gravitational forces constantly stretch and squeeze Venus as it orbits the Sun, creating tidal effects so complex and subtle that they might hold the key to understanding how the planet acquired its impossibly slow, backwards rotation. These tidal forces operate through mechanisms that are fundamentally different from the familiar ocean tides on Earth, involving the solid body of the planet itself and its massive atmosphere in intricate gravitational dances that can alter planetary rotation over millions of years. Tidal forces arise because gravity decreases with distance, meaning that different parts of a planet experience slightly different gravitational attractions toward external bodies like the Sun. For Venus, the side facing the Sun experiences stronger solar gravity than the planet's center, while the side facing away from the Sun experiences weaker gravity, creating a stretching effect that slightly deforms the planet's shape and creates internal stresses throughout its structure. Dr. George Darwin's pioneering research on tidal theory, building on his father Charles Darwin's work, revealed that these tidal deformations don't just create temporary bulges, but can transfer angular momentum between planetary rotation and orbital motion over geological timescales. For Venus, these tidal interactions with the Sun are particularly complex because they involve both solid body tides and atmospheric tides operating simultaneously. The solid body tides on Venus involve deformations of the planet's rocky interior as tidal forces squeeze and stretch the planet twice per orbit. These deformations are small, typically only a few centimeters in amplitude, but they involve the motion of enormous masses throughout Venus's interior, creating internal friction that can dissipate rotational energy and gradually change the planet's rotation rate. Recent calculations by Dr. Jacques Lasker at the Observatoire de Paris show that solid body tidal dissipation on Venus operates much more slowly than similar processes on Earth due to Venus's greater distance from the Sun and different internal structure. However, over billions of years, even weak tidal effects can produce substantial changes in planetary rotation, potentially contributing to Venus's current slow rotation rate. Atmospheric tides on Venus represent a more complex and potentially more important mechanism for rotational evolution. Venus's massive atmosphere responds to solar heating by expanding and contracting in patterns that create moving atmospheric bulges around the planet. These atmospheric mass concentrations create gravitational forces that can interact with the planet's rotation in ways that transfer angular momentum between the atmosphere and solid planet. Dr. Pierre-Simon Laplace's mathematical analysis of atmospheric tides, developed for Earth but applicable to Venus with modifications, demonstrates that atmospheric tidal effects can be much larger than solid body tides when atmospheres are sufficiently massive and thermally responsive. Venus's atmosphere, being roughly 100 times more massive per unit surface area than Earth's, creates atmospheric tides that could significantly affect planetary rotation over geological time. The thermal atmospheric tides on Venus are driven by the daily heating cycle as different parts of the atmosphere receive varying amounts of solar radiation due to planetary rotation. However, Venus's extremely slow rotation creates thermal tidal patterns completely unlike those on any other planet. The 117 Earth day solar day on Venus means that atmospheric heating patterns evolve so slowly that thermal equilibrium processes have time to operate that would be impossible on faster rotating planets. Dr. Timothy Schubert's atmospheric modeling research reveals that Venus's slow rotation allows atmospheric thermal tides to develop more fully than on faster rotating planets, potentially creating stronger coupling between atmospheric dynamics and planetary rotation. These enhanced thermal tides might contribute to maintaining Venus's current rotational state through feedback mechanisms that resist changes to the rotation period. Gravitational tides from Earth add another layer of complexity to Venus's tidal environment. During inferior conjunction, when Venus passes between Earth and the Sun, the two planets approach within about 25 million miles of each other, close enough for Earth's gravity to create measurable tidal effects on Venus. These Earth-Venus tidal interactions might contribute to the near resonance between Venus's rotation period and Earth's orbital period. Recent orbital dynamics calculations by Dr. Gwenel Moy suggest that gravitational interactions with Earth might have played a role in shaping Venus's rotation over geological time. The current Venus rotation period of 243 days creates a situation where Venus shows nearly the same face to Earth during each inferior conjunction, suggesting possible resonance capture effects driven by Earth-Venus tidal interactions. The obliquity tides represent additional tidal effects that arise from Venus's slight axial tilt. Tidal heating effects on Venus involve the conversion of tidal energy into internal heat through friction and deformation processes. While this heating is much smaller on Venus than on tidally active moons like Jupiter's Io, it still represents a continuous energy source that affects Venus's internal thermal evolution and might influence geological processes including volcanism and internal convection. Dr. Wade Henning's research on tidal heating in terrestrial planets shows that even the relatively weak tidal forces acting on Venus contribute measurable amounts of internal heat over geological timescales. This tidal heating might affect the efficiency of mantle convection and core dynamics in ways that could influence magnetic field generation and surface geological activity. The tidal evolution of Venus's rotation involves complex feedback loops between rotation rate, tidal strength, and atmospheric dynamics that can create stable equilibrium states very different from initial conditions. As Venus's rotation slows due to tidal effects, the tidal forces themselves change in strength and character, potentially leading to stable rotational states that balance tidal acceleration and deceleration forces. Recent studies by Dr. Alexander Correa on the tidal evolution of Venus suggest that the planet's current retrograde rotation might represent a stable equilibrium state where solar tidal forces, atmospheric tidal effects, and gravitational interactions with other planets balance to maintain a constant rotation rate and direction. This equilibrium might persist for billions of years despite continuing tidal evolution. Tidal despinning represents the process by which tidal forces gradually slow planetary rotation over geological time. For Venus, both solar tides and atmospheric thermal tides contribute to the spinning effects, though the relative importance of different mechanisms remains uncertain. Understanding tidal despinning is crucial for interpreting Venus's rotational history and predicting its future evolution. The comparison with Mercury's tidal evolution provides insights into how different tidal environments affect planetary rotation. Mercury is tidally locked to the Sun in a 3-to-2 spin orbit resonance, completing exactly 1.5 rotations per orbit. Venus's more complex tidal environment, involving atmospheric effects and gravitational interactions with Earth, might explain why it didn't achieve simple tidal locking like Mercury. Tidal friction coefficients determine how efficiently tidal deformations dissipate energy and change planetary rotation. For Venus, these coefficients depend on internal structure, atmospheric properties, and the frequency of tidal forcing, creating a complex parameter space that affects how quickly tidal evolution operates and what final rotational states are possible. Dr. Bruce Bill's research on planetary tidal friction shows that Venus's tidal parameters are still poorly constrained due to uncertainties in internal structure and atmospheric dynamics. Future missions to Venus might provide better constraints on these parameters through precise measurements of Venus's shape, internal density distribution, and tidal response amplitude. The tidal bulge misalignment represents the key mechanism by which tidal forces affect planetary rotation. Due to internal friction and thermal lag effects, tidal bulges don't align exactly with the gravitational forces creating them, but lag behind by small angles. This misalignment creates torques that can either accelerate or decelerate planetary rotation depending on the rotation rate and tidal forcing frequency. Recent theoretical work by Dr. Silvio Ferraz Mello on tidal dynamics reveals that the direction and magnitude of tidal torques on Venus depend critically on the relationship between the planet's rotation period and the timescales for tidal bulge formation and relaxation. Understanding these timescales is crucial for determining how tidal forces have shaped Venus's rotational evolution. The study of tidal forces on Venus provides crucial insights into planetary dynamics throughout the solar system and beyond. The complex interplay between solid body tides, atmospheric tides, and gravitational interactions from multiple sources demonstrates how tidal evolution can create planetary rotation states that are far from initial formation conditions. As we prepare to explore Venus's atmospheric superrotation and its mysterious dynamics, remember that tidal forces represent the invisible sculptors of planetary rotation, operating through subtle gravitational effects that can fundamentally alter how planets spin over cosmic time, creating worlds like Venus where the familiar relationship between day and year breaks down entirely. Chapter 5. Superrotation high above Venus's hellish surface, an atmospheric phenomenon so extraordinary that it defies every theory of planetary atmospheric dynamics, races around the planet at speeds that challenge our understanding of how atmospheres can behave. Venus's upper atmosphere completes one full rotation around the planet in just 4 Earth days, 60 times faster than the planet's surface, creating a super-rotating atmospheric shell that maintains winds of over 350 kilometers per hour, while somehow remaining dynamically stable for geological timescales. This atmospheric superrotation represents one of the most profound mysteries in planetary science because it violates the basic principle that planetary atmospheres should rotate at approximately the same rate as their planetary surfaces due to frictional coupling. On Earth, atmospheric winds never systematically exceed surface rotation speeds by more than small factors. Yet Venus's atmosphere has somehow decoupled from the surface entirely to create a separate rotational regime. Dr. Gerald Schubert's pioneering research on Venus atmospheric dynamics revealed that superrotation involves the entire atmospheric mass above, about 20 kilometers altitude, representing an enormous reservoir of angular momentum that somehow became concentrated in atmospheric motion rather than planetary rotation. The total angular momentum in Venus's superrotating atmosphere exceeds the angular momentum of the solid planet itself, creating a world where the atmosphere and surface exist in completely different rotational regimes. The mathematical description of atmospheric superrotation involves complex three-dimensional fluid dynamics operating under extreme temperature and pressure conditions. Unlike Earth's atmospheric circulation, which is driven primarily by temperature differences between equatorial and polar regions, Venus's superrotation is maintained by mechanisms that remain poorly understood despite decades of theoretical and observational investigation. Recent observations from the Akatsuki orbiter have provided unprecedented detail about Venus's superrotation through continuous monitoring of cloud motions at different altitudes. These observations reveal that superrotation is not uniform throughout the atmosphere, but varies with altitude, latitude, and time in patterns that suggest complex dynamical processes operating throughout Venus's atmospheric structure. The cloud-level winds that define Venus's superrotation reach maximum velocities of 350 to 400 kilometers per hour at altitudes around 65 to 70 kilometers, where the dense sulfuric acid clouds that shroud the planet are located. These winds decrease toward both higher and lower altitudes, creating a wind profile that suggests the superrotation is driven by processes operating specifically in the cloud layer region. Dr. Kevin McGoldrick's analysis of Venus wind measurements shows that the superrotation maintains remarkably constant speeds over timescales of months to years, despite the complex dynamics that must be operating to maintain such extreme atmospheric motion. This stability suggests that superrotation represents a fundamental atmospheric state rather than a temporary dynamical phenomenon. The angular momentum problem of Venus's superrotation involves understanding how the atmosphere acquired so much rotational momentum, and why this momentum hasn't been transferred back to the solid planet through atmospheric friction. Conservation of angular momentum requires that if the atmosphere gains rotational momentum, the solid planet must lose an equivalent amount. Yet Venus's atmospheric superrotation appears to have been stable for geological periods. Thermal tidal theory represents one attempt to explain superrotation through the interaction between solar heating and atmospheric dynamics. Dr. Pierre-Simon Laplace's original atmospheric tide theory, when applied to Venus's extreme conditions, suggests that intense solar heating of the dense atmosphere could drive atmospheric motions that gradually accelerate atmospheric rotation through thermal tide effects. However, thermal tide theory faces significant challenges in explaining Venus's superrotation because standard thermal tide mechanisms predict atmospheric accelerations that are much smaller than observed and don't readily explain how superrotation could be maintained against frictional losses over geological time. The momentum deposition mechanism proposes that solar heating creates atmospheric waves that transport angular momentum from equatorial regions toward polar regions and from lower altitudes toward upper altitudes. Dr. Thomas Girash's research on atmospheric wave dynamics shows that certain types of atmospheric waves can transport angular momentum in ways that could contribute to maintaining superrotation. These atmospheric waves, driven by solar heating and atmospheric instabilities, could create a momentum transport system that continuously pumps angular momentum into the superrotating atmospheric layers while removing momentum from lower altitude regions that are more strongly coupled to the planetary surface. Recent numerical simulations of Venus atmospheric dynamics by Dr. Masahiro Takagi have incorporated detailed atmospheric chemistry and radiative transfer to explore how superrotation might be maintained through complex interactions between atmospheric heating, chemical processes, and global circulation patterns. These simulations suggest that superrotation might result from subtle balance between multiple atmospheric processes rather than any single driving mechanism. The vertical transport of angular momentum represents a crucial aspect of superrotation dynamics because the phenomenon extends throughout a substantial portion of Venus's atmospheric column. Understanding how angular momentum moves vertically through the atmosphere is essential for determining what processes drive superrotation and how it remains stable over long timescales. Dr. Suzanne Smaraker's analysis of atmospheric temperature profiles from Venus missions reveals that the temperature structure of Venus's atmosphere creates conditions that could support vertical angular momentum, transport through convective processes, atmospheric waves, and meridional circulation patterns that redistribute momentum in complex three-dimensional patterns. The role of atmospheric chemistry in superrotation represents an understudied aspect that might be crucial for understanding the phenomenon. Venus's atmosphere contains sulfur dioxide, sulfuric acid, and other chemically active compounds that participate in reactions driven by solar radiation and atmospheric dynamics. These chemical processes might affect atmospheric density distributions and circulation patterns in ways that influence superrotation. Recent spectroscopic observations of Venus's atmosphere have revealed chemical variations that correlate with dynamical features in the superrotating circulation, suggesting that atmospheric chemistry and dynamics might be coupled in ways that affect how superrotation is maintained and how it varies over time. The comparison with other planetary atmospheres highlights just how unusual Venus's superrotation actually is. Titan, Saturn's largest moon, exhibits atmospheric superrotation that is much weaker than Venus's, while other planets with substantial atmospheres like Earth, Mars, and the giant planets show no evidence for systematic atmospheric superrotation, despite having very different atmospheric compositions and thermal environments. Dr. Imke de Peter's comparative planetary atmospheric studies suggest that Venus's superrotation might require a very specific combination of atmospheric mass, composition, thermal environment, and planetary rotation rate that is not replicated elsewhere in the solar system. This uniqueness makes Venus's superrotation both particularly interesting and particularly difficult to understand. The magnetic field implications of superrotation represent another puzzle because atmospheric superrotation should affect the generation of magnetic fields through dynamo processes in Venus's ionosphere and upper atmosphere. However, Venus has essentially no magnetic field, suggesting that superrotation either doesn't contribute to magnetic field generation or that other factors completely overwhelm any magnetic effects from atmospheric motion. Atmospheric tidal locking represents a possible relationship between superrotation and Venus's slow planetary rotation. Some theoretical models suggest that superrotation might be related to atmospheric tidal effects that also contribute to the planet's slow rotation rate, creating a coupled system where atmospheric and solid body dynamics influence each other through complex tidal mechanisms. Dr. Alexander Correa's research on atmospheric tidal effects explores how the massive superrotating atmosphere might create torques on the solid planet that contribute to maintaining Venus's slow rotation period. If correct, this would mean that superrotation and slow rotation are part of the same dynamical system rather than separate phenomena. The future evolution of Venus's superrotation represents an important question for understanding long-term atmospheric dynamics. Climate models suggest that superrotation might not be permanent, but could change over geological timescales as Venus's atmospheric composition, surface temperature, or orbital characteristics evolve. Recent studies of atmospheric escape processes on Venus suggest that the planet is gradually losing atmospheric mass to space through various mechanisms. If atmospheric mass loss continues over geological time, it might eventually affect superrotation by changing the atmospheric momentum reservoir and the efficiency of the processes that drive superrotational dynamics. The study of Venus's superrotation provides crucial insights into atmospheric dynamics under extreme conditions and demonstrates that planetary atmospheres can develop circulation patterns that are completely decoupled from surface rotation. Understanding these processes is essential for interpreting atmospheric dynamics on exoplanets, particularly those with thick atmospheres and extreme greenhouse conditions. The exoplanet implications of superrotation are particularly important because many confirmed exoplanets have characteristics similar to Venus, including thick atmospheres, close orbits around their host stars, and extreme greenhouse conditions. Understanding how superrotation develops and evolves on Venus provides crucial context for interpreting atmospheric dynamics on these exotic worlds. As we prepare to explore Venus's greenhouse hell and its role in creating the planet's extreme conditions, remember that atmospheric superrotation represents more than just an unusual wind pattern. It demonstrates that planetary atmospheres can develop their own rotational dynamics that operate independently of surface rotation, creating atmospheric regimes that follow completely different physical principles than those we observe on Earth.